Hello, this video will describe about the recent review paper on 4D PC MRI. The title is Hemodynamic Quantification using 4D PC MRI measurement of hemodynamic parameters and clinical applications. PC MRI, phase-contrast MRI measures the flow by estimating the phase difference between the reference image without bipolar gradient and the flow-sensitive images with bipolar gradient. While the reference image has no phase shift by the flow-sensitive images have velocity-dependent phase shifts. So by calculating the net phase shift, we can measure the temporal variation of the three directional flow fields. While conventional 2D PC MRI measures two scans, one without flow sensitivity and one with flow sensitivity. However, 4D PC MRI mostly requires 4 points measurements, one reference and three orthogonal velocity encoded images. From the time resolved three-dimensional, three-directional velocity information, we can visualize and analyze the complex blood flows in blood vessels, which has been difficult with 2D PC MRI. For 4D PC MRI procedures, we need to consider three steps. At first, scan parameters should be set up. Field of view, partial resolution, temporal resolution, VANC, partial K-space, parallel imaging, and so on. These parameters are closely related to the scan time and quality of the data. Under the most of the clinical environment, the scan time is limited. Therefore, scan parameters should be adjusted to maximize the data quality for the limited scan time. Secondly, once we obtain the data from the MRI scanner, we need to perform pre-processing to remove the possible errors from the low data. Phase offset corrections, phase arising correction, mask generation for ROI will be needed to guarantee the data quality. Finally, the data can be visualized and quantified depending on the needs the researchers have. The velocity and flow rate of the blood flow are one of the most basic fluid dynamic parameters assessing the normal and pathological condition of the blood flow against the baseline. The velocity of the blood flow calculated from the 4D PC MRI data is usually visualized using the path lines and streamlines with velocity color mapping for any arbitrarily cross-sectional plane within the volumetric data. Retrospective quantification of the flow rate can be carried out by integrating the velocity inside the specified lumen. Wall shear stress is a frictional shearing stress of the fluid exerting on the vascular wall. Recently, wall shear stress distribution in arterial blood flow has received large attention because it has been known to be associated with vascular disease, specifically atherosclerosis and aortic dilatation. The first step for wall shear stress estimation is to obtain smooth spline contour or surface of the lumen from the magnitude, phase, or mask images so that the wall location and normal displacement vector can be estimated from the lumen contour or surface. Then the velocity near the wall along the normal vector is obtained by interpolating and the neighboring velocity data, and the velocity gradient at the wall were calculated on the vessel lumen using the spline interpolation model, which provides the analytical derivative of the flow velocity. Consequently, wall shear stress can be obtained by multiplying the obtained velocity gradient and the blood viscosity with assuming that the blood viscosity is constant around 4 cp. Finally, the obtained Walshian stress is usually visualized using the color-mapped surface rendering to distinguish the low and high Walshian stress regions. While the blood flow is mostly laminar flow, the blood flow can be turbulent flow with high velocity fluctuation under these certain conditions. In particular, the arterial blood flows with the local contractions such as aortic valve, aortic coarctation, atherosclerosis, and so on, usually develop local turbulent blood flow. Quantifying turbulence velocity fluctuation is important because it increases the pressure drop along the vessel by elevating the fluid energy dissipation, which consequently result in more energy needed for maintaining the perfusion of the blood flow. Previously, Divefeld et al. Derived a relation for TKE estimation based on the relation between the intravoxel velocity distribution and the MO signal from a standard PC-MRI measurement. This estimation assumes that the spin velocities within a voxel are normally distributed in turbulent flow. We can estimate 3 directional standard deviation components of the turbulent flow from the magnitude images of the 4-point measurements. The blood flow frequently generates the vertical flow patterns in various vascular regions, including left ventricle, the ascending aorta, and pulmonary vessel. While the detailed relationship between the vertical flow and the pathology has not been fully understood yet, existence and intensity of the vertical flow are known to be influenced by the pathological conditions such as aortic aneurysm, pulmonary hypertension, heart disease. Therefore, the accurate quantification of the vertical flow structure is important for revealing the relationship between the vertical flow structures and the vascular disease and for developing fluid dynamic index based on the vertical flow structure. Pressure loss of the blood flow indicates the loss of flow energy generated from the heart. The increase of the energy loss results in the decrease of the blood flow or the increase in the workload of the heart for maintaining the same flow rate. Therefore, the pressure gradient is widely used as an important biomarker, indicating the severity of the stenosis such as aortic valve stenosis or aortic coarctation. Recently, the relative pressure estimation using 4D PC-MRI has been introduced as an alternative method for estimating the pressure loss of the blood flow across the aorta and stenosis. The method aims to calculate the pressure gradient at each voxel from the Navier-Stokes equation and reconstruct the pressure field over the whole vessel of interest.